independent groups design. Independence and groups. Two things we don't have anymore. Remember what it was like? You'd walk around doing stuff with friends. But we still have independent two-group designs. I guess that's something. And we'll even have independent multi-group designs before we're done. So it'll be just like old times, right? Just a sample, hanging out, manipulating a variable. Happier days. We have a lot to talk about this chapter, actually, and this topic, I suppose I should say, although it does just cover one chapter. You'll notice that we spend 4 full weeks here, which sounds insane even to me. I designed it, saying it out loud, it seems crazy. But that's because we're going to do simple experiments, multi-group experiments, independent samples t-test, analysis of variance, post hocs. There is a ton of stuff in this chapter. We're going to start relatively slowly here as we talk about what simple experiments are, what multiple group experiments are, and get our first look at calculating a single sample t-test by hand. Sort of. It's by hand, but I'm doing it here in these slides. Next week we'll do a calculation by hand together in my lecture and then in person. And then I'll also show you how to do it in SPSS, which is probably the more valuable skill, truth be told. But I'm old-fashioned. I'm old-fashioned because I'm old. People used to say, Chris, you're prematurely gray. And I said, no, I am exactly on time gray. I'm old. I'm an older fella. And being such, I like to teach the actual statistic so that you understand the purpose rather than just how to do it. I know, it's annoying. I'm sorry, but here we are. So why don't we just get started? It's actually pretty interesting stuff. How many times do you think I've said it? Hard to count that many. But when we're talking about research design and statistics, we're talking about choosing the proper tool for a job. And to that end, your textbook author has a little roadmap that she uses to kind of demonstrate how you might make that decision, kind of a decision path, like a choose your own adventure novel, but fewer vampires. And we start with this simple question. Do we have independent groups? And if we do, well, then is the variable manipulated? And if it's not, then we're talking about a correlation. Remember, a correlation is a descriptive study, actually, that describes the relationship between two variables. In a correlation, we have two variables. We have what we call the predictor variable, X, typically referred to algebraically, and Y, the outcome variable. The idea is that you can predict the outcome variable from the predictor variable. X predicts Y, because what we're doing is establishing the relationship between X and Y. Once you know how X and Y move together, to know one is to know the other. But that's not an experiment, because we're not manipulating any of those variables. We're simply describing them, and describing them admittedly more complexly by describing how they're related. So we don't need to worry about a correlation right now. So what's the next step on this path? If there is a variable manipulated, is there random assignment? Are we able to randomly assign to condition of that manipulated variable? If not, we have what we call a quasi-experimental design. We've talked about that. A quasi-experimental design looks a lot like an experiment, except that we have a variable that we cannot randomly assign our participants to. It's often some sort of participant characteristic. We talked rather a lot about this in the previous chapter, right? But I can't randomly assign you to having grown up in Boston, or having been raised by a single parent, or that you're Baptist, or that you're African American. I can't randomly assign you to those conditions, and therefore they can't be true experiments. I can't use any of those kinds of subject characteristics, participant characteristics, as an independent variable. So we have what we call a quasi-IV, one that we can't randomly assign to, and then of course a DV, which we measure at the end. But we're not talking about quasi-experiments today. We're talking about experiments. And experiments require They are, by definition, a study in which we can manipulate a variable and therefore we can randomly assign participants to conditions of that variable. So an experimental design has a true independent variable and a dependent variable. I remind you, the idea is that we manipulate the independent variable to see how it changes, potentially, the dependent variable. The dependent variable is called that because it's thought to be dependent upon the manipulation. The dv will change as a function of the manipulation of the independent variable. That's the idea. So this is what we're going to talk about. A couple of versions of true experiments. Let's start with the simplest. The simplest is called the simple experiment. Well, that's handy. It's nice when the packaging matches the contents. This is the simplest experiment. It's a simple experiment in which the independent variable is manipulated, but it is a single independent variable. Notice that. And we've always just talked about one. But it turns out you can have studies, experiments with multiple independent variables. We call them factorial designs, because the word factor is another word we use for independent variable. So factorial means you have multiple factors or multiple independent variables. Honestly, that's where things get really interesting, but it's also where things get really complicated. So we won't talk about that yet. The other thing required of a simple experiment is that the participants are randomly assigned to one of two levels of the independent variable. There are just two groups. You take your independent variable and you create two versions of it, two conditions of it, and then you assign your participants to one of those two conditions. So it looks something familiar. We'll see it here in a second. And then finally, a dependent variable that is measured to test the effect of the IV. Again, the outcome variable, the dv, is thought to be dependent upon that manipulation. So if you have these three things, you have a simple experiment. And it looks very familiar because we use the simple experiment as our example all the time. We take our group, it's been randomly selected from our population. Then we randomly assign them to two conditions. I hope you'll forgive me, but I decided to use a vaccine study as an example. One group is given a vaccine, one group is given a placebo. And then we measure their physical symptoms. Do they have symptoms of a disease? Whatever the disease the vaccine is treating, you can imagine what I was thinking about. And then we see if those two groups are equal when all is said and done. The idea is quite simple, right? If the vaccine worked, they shouldn't be equal. The vaccine group should be healthier than the placebo group because it prevented the illness. If they are equal, well, then it seems as though that placebo was equally effective of the vaccine. Or in other words, the vaccine doesn't do anything. The trick, of course, is when we get done and the numbers aren't the same, are those numbers real? Is that difference real? Is it due to that manipulation of the independent variable or simply sampling error? That's why we need statistics. But this is the basic design. This is the simple experiment. Let me show you a slightly more complex experiment, still with just one independent variable. But you'll see it's a little more complex. As I said, still just a single independent variable that we're going to manipulate. But now we're randomly assigning our groups to two or more levels of our independent variable. I highlighted it in red. That's how you know it's important. Look, I took our previous example and I altered it. Instead of just a vaccine versus placebo group, now we've got three groups. Placebo, 150 milligrams of the vaccine, and 300 milligrams of the vaccine. I know vaccines don't really work that way, but it's a kind of a drug-dependent model here. And then we can see if those three groups are different from each other. This is actually a really important detail. But we can see if the placebo group differs from the 150 milligram group. We can also see if the placebo group differs from the 300 milligram group. We can see if the 150 milligram group differs from the 300 milligram group. So there are actually three different comparisons we can make. We compare sample 1 to sample 2, sample 1 to sample 3, and sample 2 to sample 3. 3 different things we can test here. That turns out to be really important in terms of kind of conceptualizing and understanding how this kind of experiment works, and honestly, more importantly, how the statistics used to analyze them work. So to look at the title of this slide, one might conclude that there are some advantages to this second version of an experiment over the first, and it's true. There are at least 4 presented by your textbook author. I think there are probably a few more, but 4 will serve for now. To be honest with you, though, some are easy, some are hard to understand. We'll see if we can make sense of them here, but we're going to return to some of them later when we talk about the statistics. The first is really easy to understand. It's just a simple issue of efficiency. If you wanted to understand the difference between 300 milligram, 150 milligram, and placebo, you could either do it in one experiment, or you could set up 3 separate experiments where 300 is compared to 150, 300 is compared to placebo, 150 is compared to placebo. You get the idea. It's much more efficient to have all of that happen in one experiment over 2. And it allows us to decrease the number of participants, decrease the number of studies. So it's just easier logistically. It's literally easier. What else? Well, you can also control confounds better. Because when we have a simple experiment where we have just vaccine versus placebo, one confound is the amount, the dosage. So by including that as part of our independent variable, by having the different doses, we can control that and understand that. Our slide, coming from our textbook, says you can have multiple control groups, and that's one way you can think about it. It's not just vaccine versus placebo, but it's amount of vaccine, varying amounts of vaccine versus placebo. Gives you a lot more information, and therefore helps you maintain your internal validity. To that same point, it also gives you a much more realistic look at the information, something that's much more likely to apply to the real world. We've been talking a lot about internal validity because we're interested in our design, but I remind you that external validity is how generalizable it is. How reflective of the real world is it? And so knowing about the dose provides us with a lot more information that we can then apply in reality. If we only tested one level of the vaccine, well, maybe that's the best level, maybe it's not, we don't know. So we can't really generalize that information. And then one final one, which is, for my money, the most interesting one, but it's also the most complex one. We're going to spend some time talking about it again later, but I want to bring it up here. Is that when you do a multiple independent groups design, you decrease the probability of type 1 error. A couple things. What's type 1 error? I remind you that type 1 error is the probability of rejecting the null hypothesis when the null hypothesis is true. And that's equal to our alpha level. Alpha equaling 0.5, typically that means our probability of making that mistake is 5%. Because we've taken that null distribution and take the most extreme 5% and made that our line. So alpha equals our probability of type 1 error. Okay. So what difference does that make? Well, here's the thing. If you do 3 different experiments to test the dosages, meaning you do a simple experiment 3 times. 300 versus 150 is the first one. 300 versus placebo is the second one. 150 versus placebo is the third. You've done 3 different simple experiments. Each one of them has an alpha level of 0.5. So the probability of each one of those experiments being in error, a type 1 error, is 5%. But you've done 3, which means the chance that you made a mistake somewhere along the way is 15%. 5% plus 5% plus 5%. Every time you carry out an experiment, you have an accumulation of that probability of making that type 1 error. So when we use a multiple independent groups design, we can do all of that at once. It's 5%. Rather than doing it 3 separate times, 15%. 15%, that's a high chance of making a mistake. If you had a 15% chance of leaving your house and getting COVID, you wouldn't go, right? 5%, you still might not, but you'd like your chances better. So one of the things we can do is create these multiple independent groups designs so that we're testing everything we want to test inside one single experiment, holding our alpha level at 0.5. We're going to talk a little bit about that in the context of one of the articles we're going to read. I'm going to say a word. It's a name. It's an Italian name. I want you to remember it. I won't tell you what it is, though. And that name is Bonferroni. Think about beefaroni. I shouldn't say that. I know a lot of our students are Italian, but I love Chef Boyardee. Still to this day. I grew up poor. Cut me some slack, but I still love it. Beefaroni was always my favorite. This is Bonferroni. We'll talk about that soon. So, what about this? You recognize the artwork from your text. They have a very specific style, don't they? But the question is, what is the impact of cell phone use on driver distraction? So what we do is we take a group of Rhode Island drivers and we randomly assign them to 2 conditions. One condition, they have a phone that is visible while they're driving. And the second, they do not. So again, one group has a phone, one group does not have a phone. And then we have a dependent variable, and it's a bit of an odd one, I have to admit. The dependent variable is how quickly or how slowly someone honks at them while they're driving. A better way to say it is the latency. How long does it take for someone to honk at the driver? If they have a phone visible, is it different than if they don't? Our null hypothesis and alternative hypothesis look like this. The null. There's no difference in time to honk between cell phone and no cell phone groups. And the alternative. There will be a difference in time to honk between cell phone and no cell phone groups. I want you to notice here. The null hypothesis describes what we'd expect if our IV had no effect, if phones don't matter. Our alternative is the opposite, what we would expect if they did. I also want you to notice that it's a two-tail hypothesis. They're not predicting the direction, they're only predicting that there'll be a difference. These are our research hypotheses, which can then be summarized as statistical hypotheses like these. The null, mean 1 equals M2. And the alternative, mean 1 does not equal mean 2. If there's no difference, they should be the same. If there is a difference, they should be different. Simple as that. So let's use the data presented by your textbook author. And here it is. We have the means, the standard deviations, the variance, and the n size for each of our conditions. The driver with no cell phone had a mean latency to honking of 7.7 seconds. The group that had a cell phone was faster, 5.2 seconds. And again, you see the variance and the standard deviation for them as well. So using this data, let's walk through the calculation. So let's start with the formula. Here's the formula for t obtained, and it looks very similar to the single sample t, except that instead of a sample mean and a population mean subtraction, we're subtracting mean 2 from mean 1. They're both sample means in this instance. And you'll also notice that in the denominator, that's not just a standard deviation, that's something else. I'll say what that something else is here in a second. So we have in the numerator, the mean of group 1 minus the mean of group 2. And then in the denominator, we have this weird thing, SD subscript x minus x. And it really, most places would list it as x1 minus x2. What that is called the standard error of the difference. And it's the average variability and sampling distribution between the means. We take the variability of one group and the variability of the second group, and we see how they differ on average. So that's not an easy calculation. So we need to see how to do it. It actually looks like this. To calculate the standard error of the difference, you take the square root of something called the pooled variance multiplied by 1 over n1 plus 1 over n2. What is the pooled variance? Well, pooled variance is actually the variance of group 1 combined with the variance of group 2. And then we're multiplying it by their individual n size. What this really is just the average variance. But it's a grand average, meaning it's being adjusted for the n size. You may have classes where your grades are weighted. That's how it works. The numbers are weighted differently based on some criteria. In this case, they're weighted differently based on how many participants are in each group. So the pooled variance is the estimate of the total variance of the group 1 and 2 combined, pooling them together. Just like pooling your money to buy a pizza. You have $3, that's not enough. You and your buddies put all your money together. Now you have $15. You've pooled your money. This is the pooled variance, the variance from the first group coupled with the variance of the second group. So how do you calculate pooled variance? N1 minus 1 times variance, or standard deviation squared, plus N2 minus 1 times standard deviation 2 squared, all over N1 minus 1 plus N2 minus 1. Not a really big deal. You're just going to take the variance of each, calculate the average, adjusted by n size. So if we're going to do this, these are the steps we take. To calculate T obtained, first, you calculate pooled variance. Then, calculate standard error of the estimate, and then calculate your T obtained. So I have your formula here along with the data so we can kind of look at it all at the same time. T obtained equals M1 minus M2 divided by the standard error of the estimate. Let me move this over. The first thing we're going to do is calculate the pooled variance. Here's the formula for pooled variance, and I've started to plug in the numbers here for you. N1 minus 1 is 10 minus 1. Standard deviation squared for group 1 is 2.04 squared. And then we see 3.06 squared times 10 minus 1 for the second group. All of that divided by 10 minus 1 plus 10 minus 1. That leaves us with 37.4 plus 84.24 over 18, or 6.76. So our pooled variance, the combined variance between group 1 and group 2, is 6.76. With that value, we can then move on to calculate the standard error of the estimate. So let me move that over. The formula for standard error of the estimate is that pooled variance score multiplied by 1 over n plus 1 over n, all square rooted. So that's the square root of 6.76, we just figured that out, over 1 over n1, 10, plus 1 over n2, 10, equals the square root of 1.352, which gives us a standard error of the estimate of 1.16. There's our numerator. There's our denominator in our formula. So let's pop that over. So we've got everything we need. Let's go back to the original formula. We've got that 1.16 in the numerator, in the denominator. I keep doing that. And now we put mean 1 and mean 2 on top. 5.20 minus 7.70 equals a negative 2.5 divided by 1.16, or a T obtained value of negative 2.15. That's our T obtained. That's our score, or standardized score, that we can use to see if it belongs on our distribution of the null. But first we have to calculate or determine our T critical. The T critical is very easy to figure out. The first thing you need to know is what your degrees of freedom are. And every single one of these, we're going to have to figure out the degrees of freedom, but every single one of them will have a different degrees of freedom formula. The one for independent samples t-test is very simple. It's n1 minus 1 plus n2 minus 1, which in this case, as we know, is 10 minus 1 plus 10 minus 1, or 18. So our degrees of freedom are 18. I'll pop that over. Step 2, we're going to use the table. In this case, it's table 10.2. So I'll bring up table 10.2 here. We're going to select our alpha level, and unless you're told otherwise, it's alpha equaling 0.05. We already said this is a two-tailed test, so you see alpha 0.05 at the two-tailed test, and then you drop down until it meets the line on the left for degrees of freedom. You see the 18, the two lines converge at 2.101. So our T critical value is 2.101, which we're then going to place on the distribution of the null. Here it is. I remind you that the distribution of the null is what the data would look like if our IV had no effect on our DV. In other words, this is what it would look like if it was simply sampling error that caused any difference that we find. So we place those values on the border of our region of rejection. That represents the most extreme 5% of this distribution. And we see where our t obtained falls. You may have forgotten already, but our t obtained was negative 2.15. Right there. It's pretty close. But negative 2.15 falls in our region of rejection. That means that it's unlikely, too unlikely, for it to belong on the distribution of the null. And if it doesn't belong there, then, well, we're going to reject the null hypothesis. In other words, we're arguing that our null hypothesis is not supported. We're going to reject it, which means we think our independent variable, talking on a phone, does make a difference in the latency for honking for distracted drivers. We say that it's statistically significant, that difference between 7 and 5 is real and not just sampling error. When we have statistical significance and we reject the null hypothesis, this is how we write it. We say t parentheses 18, that's the degrees of freedom, equals the t obtained negative 2.15, comma p less than 0.05, where 0.05 is our alpha. T, degrees of freedom, equals t obtained, comma p, and then our alpha level. If we reject the null, it's less than 0.05. If we fail to reject the null, it's greater than 0.05. So we did it. That is an independent samples t-test. So after not much of a summer, I've decided to just kind of live in this can of White Claw, so you can see the bubbles of the grapefruit spritzer surrounding me. And that's why that lecture went so quickly, I suppose. I hope you enjoyed it. We're going to kind of take this tact. We've got a whole month on this one chapter. I know it sounds nuts, but there's so many important things here. So we're going to do conceptual, then we do hand calculation in SPSS, and we're going to do that. We just did the conceptual for the t-test. I'll walk through by hand next week the independent samples t. Then we'll do the same thing again for ANOVA, which is so important. It's really the granddaddy of all the statistical tests. Analysis of variance. It shows up in 75% of every paper you'll ever read. So it's just a really impactful and important time in the class. And so we're going to take our time and make sure that this stuff really sticks. And then when you take the experimental courses in your junior or senior year, you're going to be a rock star. That's the idea, at least. That might be the White Claw talking. All right, I'm going to drink my way out of this, and I'll see you later. Bye.
Some might find they're weaker, some stronger than they thought. Well, I stand or fall right here in my country, in my home. I used to think I was alone, well, I ain't alone no more. Back spotter, heart attack machine. Back spotter, heart attack machine.